Good morning, one and all. Respected CED Sir, Dr. Shashidhar Muniappa, SVGI Bengaluru, respected Principal, Dr. Suresha, and Chairperson of STTP Program, Shri Venkateshwara College of Engineering, Bengaluru. Resource person of the session, Mr. Shashidhar Artham, Senior Staff Engineer, Audience Communications, Bengaluru. Dr. Shivshankar, Professor and Head of the Department of Electronics and Communication Engineering and convener of the short-term training program. Participants, learned delegates from corporate and academia, a very good morning, one and all. I am Sarlati, Assistant Professor, Electronics and Communication Engineering Department, and I feel privileged to extend a warm welcome to you all on behalf of Department of Electronics and Communication Engineering, Shri Venkateshwara College of Engineering, Bengaluru, to the AICTE sponsored short-term training program under AQIS Program A on optimization techniques for 5G cellular networks, compressive sensing, and data science using MATLAB. Second week STTP on compressive sensing techniques for 5G cellular networks using MATLAB from 22nd to 27th July 2020. We have successfully completed the first 1 week AICTE sponsored short term training program under AQIS Program A on optimization techniques for 5G cellular networks. 11 technical sessions were delivered by eminent personalities with more than 600 views on our broadcast YouTube channel STTP ECE SVCE. On this occasion, we thank specially AICTE for sponsoring, motivating, and supporting the splendid events like this. I would like to thank management and principal of Sri Venkateshwara College of Engineering for their support and encouragement for conducting this STTP. From this STTP, we are going to learn about 5G. 5G is not only important because it has the potential to support billions of devices at ultra soft speed, but also because it has the potential to transform the lives of people around the world. 5G can power technology well beyond what current mobile technology permits. This short term training program enables the faculty members in the field of technical education to introspect and learn techniques that can help prepare students for active and successful participants in the knowledge society. In this regards, I'd like to welcome our beloved Chief Executive Director, Sir Dr. Shashidhar Muniappa, Sir, SVGI, Bengaluru, for this elite event. Because of Sir's busy schedule, Sir couldn't join for this session. Sir, however, conveyed his best wishes for the event conduction. Now, I'd like to welcome our beloved Principal, Dr. Suresha, Sir, SVCE, Bengaluru, for this elite event. Because of Sir's busy schedule, Sir couldn't join for this session. However, Sir conveyed his best wishes for the smooth conduction of the event. The building of this event is not happened in a single glance. Enormous effort of the team, extensive support from the elders, and fabulous synchronization by our beloved head of the Department of Electronics and Communication Engineering, Dr. Shivshankar sir. I'd like to welcome you, sir, for this elite event. Now, I'd like to welcome resource person for the session, Mr. Sridhar Artham, Senior Staff Engineer, Audience Communications, Bengaluru. Welcome you, sir. I am privileged to welcome all the participants for this event. May I now request our beloved Head of the Department, Electronics and Communication Engineering, Dr. Shivshankar sir, to give a brief overview about the short-term training program.
Very good morning to one and all present. First and foremost, I would like to express my sincere thanks to AICT for their support to conduct this type of events in our institute. on behalf of Sri Venkateswara College of Engineering, Principal and the Department of Electronics and Communication Engineering, staff and student. Once again, I will express my sincere thanks to AICT. So just last week, we have completed 1 week STTP program on optimization techniques for 5G cellular network. So successfully, we have completed this 1 week program. So in this regard, I would like to express my sincere thanks to my dedicated team members. Thank you all. So in these 6 days, so my research scholars and eminent personalities are going to present their knowledge about compressive sensitive techniques for 5G cellular networks using MATLAB. So recently in a MATLAB, there are a lot of library functions related to communication and 5G networks are available. So eminent resource persons are going to present in front of you. So how to implement the program means how to implement the algorithm, how to test it, how to validate your research work or any work related to 5G using MATLAB. They will present you. And a compressive sensitive technique not only for 5G cellular network, so it is related to signals, image processing, artificial intelligence, etc. So from day one, we are seeing in the digital signal processing. So compressive techniques actually the basic principle of sampling theorem and quantization techniques. So along with these techniques, what are the related research works are going on till today. So you will get all this information. My dear participants, I will request you one thing, just for shake of certificate, don't attend this HTTP program. So try to gather more and more information about compressive sensitive techniques for 5G cellular network. So you will study both theory and the practical sessions in these 6 days. So make it grand success. I wish you all the best for both participants and coordinators. Be safe, take care. Thank you.
Thank you very much, sir, for your thought-provoking address set a perfect platform for our speakers to deliver their presentations in the area of compressive sensing techniques for 5G cellular networks using MATLAB. Dear all, now we'll begin with the technical session one by Mr. Sridhar Artham, Senior Staff Engineer, Audience Communications, Bengaluru, to introduce Sir in brief our esteemed audience. Mr. Sridhar Artham completed his master's from NIT Rourkela in the Communication System branch. Sir has total of 15 years of industrial experience. During his 15 years of journey, he worked on various fields such as digital signal processing, audio, speech processing, codecs, real-time OS, embedded system, platform experts, ARM, IT, QDSP, and Tensilica processors. Optimizations on various real-time platforms like Exynos processors for Samsung, Snapdragon chipsets for Qualcomm, and various other customized chipsets. He started his career while pursuing his master's as project trainee in Donla Technologies. After completion of his master's, he started working in HelloSoft India Private Limited. During this tenure, he expertise in floating fixed point conversations, ARM porting of speech codecs, speech enhancement algorithms like one mic noise suppressions and echo cancellations. Later, he continued his career in Wipro Technologies as senior software engineer, where he worked on audio codecs optimization. Then he moved on to NXP Semiconductors as technical architect. During this period, he worked on development of speech audio codecs, speech audio processing algorithms, platform optimization on ARM, QDSP, and Tensilica cores. He is currently working in audience communications as senior staff engineer on development of audio processing algorithms, design of new platform architecture for audio processing, and customer engagements. With this brief introduction, I'd like to welcome you, sir, once again for this Elite event. Now, I request our resource person, Mr. Sridhar Artham, to take over the session on compressive sensing and multimedia signal processing for 5G.
Thank you, madam, for the introduction. Good morning, everyone. I would like to first thank SVCE for conducting these sessions, and I also thank Department of Electronics and Communication Engineering (SVCE) for taking the efforts to make it a grand success. I wish uh, I wish all the people to understand, to learn the concepts of this session, and make it because the 5G is still under development activities itself. So I hope these sessions will really help in providing the proper and know-how in the 5G technology. So let me start my presentation. I hope the screen is visible.
No, sir, not yet. Screen is not visible.
Is this visible now?
No, sir. Now it is visible.
Okay. Okay, let me start with my session. So my topic for the discussion is on compressive sensing and multimedia signal processing for 5G. So
Sridhar, sir?
yeah,
Sir, can you make it as full screen?
it is full screen itself.
Slideshow.
Yeah, it is a slideshow only.
No, it is.
Wait a minute. Is it full window now?
Wait, sir, not yet visible. Yeah, now it is visible.
It's fine,
Yeah,
right?
yeah, sir. Yes.
Yeah. Thank you. So let me start the introduction of this compressive sensing and multimedia signal processing. Today, my topics, what I will be going to cover is basically I will be introducing the key features of 5G and what is the compressive sensing and what are the principles behind the compressive sensing and how we are applying this compressive sensing to multimedia signal processing, and then what are the various DSP architectures required in order to realize these compressive sensing techniques in the real-time scenario. And then I will make a walkthrough on the architectures which are related to the realization of this compressive and multimedia techniques for the 5G networking. So basically, like 5G is a vast ocean, I can say, because we cannot cover all the things in one shot. So I'll be keeping my discussion brief or narrowed down to the compressive sensing technology and the application of this compressive sensing technology to the multimedia signal processing, which are used in the 5G networking communications, and focusing mainly on the audio and speech, because video, it is a kind of, it will take its own time, and so since we have the limited time, let us scope only on this topic so that we will have the thorough and good understanding of this technology. So I'll be discussing the key features which are relevant for the compressive sensing and application of the compressive sensing techniques to the multimedia signal processing. So I'll not be going beyond these features because there are many features related to the networking and the hardware related stuff, all that one. So which will be kind of irrelevant for the discussion. So in the optimization techniques are previously, it might be like, might have discussed all those things. So the key features which are relevant for our discussion are, if you see the 5G network, it offers very high speeds of data, like they're touching to the high peaks. I can say like it is going up to 10 Gbps per second. So it offers a very huge amount of data rate. That is one of the key feature of the 5G. So because of this high data rates, there is a extension of the bandwidth for the spectrum. So the bandwidth, in the sense like the extension of the bandwidth, what does that mean is basically, if you see from 2G, 2.5G, 3G, 4G, so the signals has started from narrow band to wide band to super wide band, and then full band. This is what the bandwidth evolution of the over the period of time. So as we increase the bandwidth, so you will have the more data which is present in that one, and means you can incorporate more amount of data, more amount of samples into that one, so that we will not be missing any of the content which is present in the data. So the 5G offers this extended bandwidth for the spectrum. And then because of this high download and upload limits and high bandwidth, there is it offers the very high resolution of data. So for making use of this high resolution of data, you require huge amount of bandwidth and huge amount of data rate speeds. So what is this resolution of the data means? For example, we'll take a simple example such that it will be very easy to understand. When you do a sampling, PCM samples, means like speech samples, when you convert into a digital domain, you have to represent in terms of bits, like 16 bits, 32 bits, and 64 bits kind of stuff. So as this resolution increase, it means that the amount of representation for the each sample will be increased. So far, the PCM samples, whatever we are using in our communications, it's on the 16-bit data width. So this high resolution means that we'll be representing the same data with the higher number of bits, so that the resolution or the quality of the signal will be more. Even the same for the video as well. Like if you take the cameras, the pixels, so if you increase the amount of pixels, what will happen is like it will be with the more resolution. So for the more resolution of data, if it has to be transmitted through the channel, it requires the high bandwidths. So as there is an increase in the bandwidths, in turn or indirectly, it is offering the high resolution usage of the data. And one more key feature of the 5G is it has the backward compatibility 4G, 3G, 2.5G, and 2G. So without that, it will be very tough to handle, because just 5G means it is a lot of hardware upgrades and everything will be there. Simply in one shot, we cannot remove all the backward compatibility. So it also offers the backward compatibility to these all previous networking standards. With these extended bandwidths and high resolution of data, there is it also provided enhanced multimedia signal processing, like audio and video processing. Multimedia is nothing but audio and video. So because of it is offering of all these features, so we will have the enhanced multimedia data which is present in the 5G networks. And one more key feature of the 5G is devices will become more interactive. So what do you mean by this more interactive? Means like there is a machine and a human being communication will be more interactive. So the human being, whatever he speaks, the machine will understand properly. That's what it's a kind of a more interactive. So what will happen with this one is like you will be in a position to use the hardware in a very efficient way. So you can wake up, or what I mean to say here is like you can control the IoT devices using your voice commands. So because of this high extended bandwidths and high resolution of data and other features of the 5G, this will become more prominent in the 5G networks. So going on, I'll be discussing in deeper on all these topics. So the features, whatever has been introduced as part of the 5G, it also brings the key challenges, how to mitigate those things. So the key challenges, what I see is here, like when we say that 5G offers backward compatibility with the 4G, 3G, and 2.5G or previous networks, it brings a lot of complexity in the system architecture. It takes good amount of time. It is a time consuming process. It is not that much simple to have the backward compatibility with the previous networking. So that is one of the key challenges in the 5G networks. Another one is that even though the bandwidth, they have given very huge bandwidths, but how do you utilize that bandwidth? Because simply based on the Nyquist criterion, if you say that I can simply sample my speech signal at 48 kilohertz, is that really helpful for us? Are we really utilizing the bandwidth? Because one of the key feature of the 5G is that even you have to incorporate more number of users into the spectrum. So if you don't use the bandwidth efficiently, we will not be in a position to incorporate those extended number of users into the network. So one of the key challenge here is like how we can utilize the bandwidth so efficiently. Since the 5G offers multiple input and multiple output techniques, what will happen is like there will be a lot of cell towers or lot of base stations will be there, so they will be very nearby. So if you want to steer the signal or if you want to focus the signal, so it will become a challenging aspect in the 5G networks. Even though beamforming is a technique which we use to steer the beams, to have the proper setup with the base station, these techniques are not so very well developed. Still, there are a lot of problems, inherent problems are there. So this is also one of the key challenge in the 5G network. And then, as I mentioned, that the devices will become more interactive. So definitely what will happen is like there will be massive machine communications will be there. So there will be a lot of communications with the machines. How do you handle? How do you control? Because security things comes into picture, many things, many aspects. So that will become that will also be a kind of one of the key challenge in the 5G networks. And one more important feature of the 5G is that it offers very low latency communications. So how do you realize in the real-time scenario? So what are the methodologies adopted in order to realize this low latency communications? That will be a kind of a challenging thing. So now when it comes to when we say that the audio and video has been, the resolutions has been introduced, and then there are a lot of enhanced processing techniques will be there where the user will have the more impressive listening to music and seeing the videos. So it comes with its own challenges, like virtual reality is one of the key feature in the 5G for the multimedia domain. Like virtual reality is like you will be seeing a kind of a virtual things as if it is a real kind of thing. In the virtual domain, you'll be seeing the whatever is happening is a kind of a real thing. And then there is a real-time speech and audio communications with the increased bandwidth. How we are going to tackle this one? Because even there is a backward compatibility is there. How we are going to handle this one? And then there is a lot of user-generated multimedia content like speech synthesis, video synthesis. Many things are there. So how we are going to handle all these things? These are all comes under as a key challenges for the 5G network. So as we go on, we will discuss one by one, and we will see that how can we mitigate and how with the compressive sensing how the compressive techniques will enable these issues and how it resolve these things using the compressive techniques. Now, before entering into the details of how we are going to mitigate and all that one, let us understand what exactly is the compressive sensing. So the compressive sensing is basically, it is a kind of a sensing means it is nothing that even a sampling is also kind of a sensing. How you are collecting the data, that is a kind of a sensing. So the whole technique or the definition of the compressive sensing, if you put in a single statement, it is that representation of the signal using very low number of samples and the way how to recover it. That is the definition of the compressive sensing in a single statement. So how do you represent a signal in a low number of samples? So as we all know that from the Nyquist criteria, Nyquist sampling theorem, what we know is that if you want to reconstruct the signal, you have to sample it twice the bandwidth or twice the highest sampling content which is present in the signal. That is what we know. So if you want to represent, or if the signal is represented with a less number of samples than the Nyquist criteria, what will happen is like we will not be in a position to recover it. But this compressive sensing technique, it will allow to recover the signal and to represent the signal with a low number of very low number of samples, I could say, like maybe like 10 times lesser than like what Nyquist is there. For example, if our speech signal, let us take the narrowband signal. So narrowband signal is nothing but the bandwidth is around 3.5, 3.4 kilohertz, and we are sampling at 8 kilohertz. So it is not required to sample at 8 kilohertz. If we use the technique of compressive sensing, we can sample at very low rates, like even lesser than the bandwidths, I could say. That's what this compressive sensing will happen, will offer to us basically. So what exactly what it is compressive sensing is offering for us? It offers the optimal acquisition of the signal and reconstruction. So basically, like, what is this optimal acquisition is that, as we know that signal can be represented with very low number of samples. When you are in a position to represent the samples in a very low number, what will happen is, like, your signal acquisition, it is nothing but sampling, I could say, in our terminology. So the signal sampling can be reduced a lot. So overall what will happen is your hardware cost will come down. When you are sampling at very low rates, as I said, that hardware cost will come down, and then overall power consumption will come down, and the signal representation or storage space, whatever is required for that one, it comes down. So this is one of the major feature or impressive feature for the compressive sensing technique. So what is the major property of the signal? If at all, if we want to represent any signal in the compressive sensing domain, what exactly it requires? It requires the properties of the signal sparsity and incoherence. So let us discuss a little in brief on this. What is exactly the signal sparsity and incoherence? Sparsity is nothing but the more number of zeros, means like where the signal is sparse signal is nothing but there will be very less number of samples present in that one. So the signal should be sparse. So people can have a doubt how the signal will become a sparse, because if you talk the day-to-day whatever speech signal, whatever, let us take a realistic example of the speech signal itself, it will not have the sparsity in the time domain. But how this compressive sensing is going to help us? So we have to find out a technique in the transform domain of the speech signal. Instead, usually, like, a speech signal is represented in the time domain. If it transform into some other domain, if the signal is sparse in that one, that is called the signal sparsity. For example, let us take a simple example of a sinusoidal function. If you take a sinusoid, in the time domain you will have the infinite infinite values, and if you digitize it, basically, like, depending on the bandwidth of the signal, the sampling rate will be there. But when you transform it into frequency domain, what will happen? You will get a simple sample, one sample of a sine wave, like, it will be a delta function in the frequency domain. So the signal is sparse in the frequency domain. Like that, we have to find out the mathematical methodologies in which domain the signal is sparse. That is the first and foremost property of the signal in order to be used in the compressive sensing technique. Another one is the incoherence. Incoherence, the meaning is, like, it should be completely uncorrelated. So the transformed domain signal, when you compare with the original domain signal, that is time domain signal, it should be completely incoherent or uncorrelated. So these are the two important properties of the signal should exist in order to consider it for the compressive sensing. So what are the major steps involved in this compressive sensing? So major steps involved is, first and foremost things, we have to find out in which domain the signal is sparse. That is a mathematical technique one has to adopt, and then he has to understand, he has to evolve. For example, if you take the regular transform domains will be like Laplace transforms or Z transforms, or usually, like, for the speech communications we'll consider as a frequency transformation, which is nothing but spectrums. And if you take the image signals, we'll have some other transform domains like wavelet transforms and discrete cosine transforms, where the signal sparsity will be more in that one. That is, so we have to find out. It is a kind of an evaluation. It is a kind of a development activity. So before considering the system to be adopted or enabled with the compressive sensing, so first and foremost step is we have to find out in which domain signal will be sparse. So that is the first step involved. So then once the step is ready, means like once we know the signal is sparse in some kind of a domain, so which is the compression techniques to be used. Compression techniques means like what I could say is like once you find out that the signal is sparse, let us take in the time domain sinusoidal signal, in the frequency it became a single sample or a single delta function. So how do you compress that one? Compress is nothing but basically you are representing the same already sparse signal, how you are compressing, like using Hoffman coding or some other lossy compression techniques. Hoffman is a lossless compression technique. So how do you represent? That becomes the sparse signal compression techniques. So once you have these two things, step 1 and step 2, finding out the sparse transformation and then representing of this sparse signal in the compression domain, and this will be transferred to the receiver side. The receiver, what it will do, it will has to regenerate the signal using this sparse signal or whatever signal has been transferred to the receiver. So that is what the sparse signal recovery. So these are the three major steps involved in this compressive sensing. So I'll not be going beyond the algorithms here, because the algorithms like it's like still in a under development, I could say. There is no proper uh, hard and fast rule. We can say that whether the compressive technique can be possible to adapt to one system or not. It requires its own time. So it is still under a research kind of stage. Now I think we are clear on this compressive sensing techniques. It means the compressive sensing, what exactly it means and what it is offering. So now let us see the applications of the compressive sensing. So where we all use this compressive, it has if you ask me, it's a very huge, which is a very tough question to be answered. The reason is like it can find out anywhere, actually wherever we are seeing the issue in representation, wherever we want to optimize, we can apply this compressive sensing technique over there. So one of the key things means like some of the key things, at least in the 5G perspective, where it can be used, we can utilize in the cameras. The cameras, what we do, so basically like we will take a pictures or we'll do some recording, video recording. So if you want to have the very high resolution of data, it requires huge amount of sampling, huge amount of storage space. Because of this, overall power consumption will be more. So if we apply the compressive sensing technique in the camera system, what will happen is like overall these reduction in the power will happen, computational complexity will come down, and overall storage space will be utilized efficiently. So that is one of the application of the compressive sensing technique in the cameras. It's like the mobiles, whatever we are using, which is very well equipped with the cameras nowadays. So if you want to have the very high resolution of data or very quality data, what we can do is we can apply the compressive sensing techniques in the taking the pictures and then storing or transmitting to the receiver. So this is one of the application in the 5G I could see to have the efficient utilization of the bandwidths. Another one is the medical imaging. If you take the medical imaging, means like basically like magnetic resonance images or angiograms, what exactly it will do is like basically it is a kind of a technique to find out the physiological or anatomical issues which are present in our body. So for that one, our body will be exposed to radiations. So you will not be having the complete data to analyze what is happening or what is a problem in our body, kind of thing. So using this compressive sensing technique, as I mentioned, compressive sensing technique is nothing but it will be applied where the signal is sparse, where you have the very less number of information, because by seeing itself you will see that okay, it has very less amount of information. So if we apply the concept of that one here, where you will have the very less amount of data in MRI and angiograms, we can utilize this compressive sensing techniques in order to reconstruct the signal where it is missing. For example, we might be missing in the actual domain, but when we transform it and when we reconstruct it using the compressive sensing domain, what will happen is like you will be retrieved with the unknown things or unknown information present in the MRI outputs or angiograms. So this is one of the application of the in the medical imaging. And if you take the even earthquakes, like when we want to analyze the data for the seismic is nothing but earthquake related stuff. So vibrations of the earth. So there also you'll have the very less amount of data. So if you want to reconstruct or if you want to reconstruct the outputs in order to have the proper information, there also we can use our compressive sensing techniques in order to retrieve the missing information present in that one. And one more important thing where we can use this compressive sensing technique in 5G is in the cognitive radio. Basically, cognitive radio is nothing but when you have the more number of different kind of networks like 4G, 3G, or some other Bluetooth or whatever it can be. Okay, if at all, if we want to choose a best networking channel for the communication, cognitive radio will help over there. But if you want to use the network spectrum efficiently, so cognitive radio, the inherent feature of the cognitive radio is it has to sense which spectrum is free, which spectrum is very less prone to channel noise errors. So all those things will be a part of the sensing techniques of the cognitive radio. So this compressive sensing technique, if we apply over there, where you will have the very less amount of data to understand what is happening in the channels, because you cannot load the loaded channels. For example, already the spectrum might be already fully used or utilized by the users. Now, once again, if you want to understand, if you want to sense it, whether the signal can be transmitted using this channel or not, so the cognitive radio, it has to rely on some techniques. So if it is adding more data in order to understand what is happening in the channel, it will add more overload to that one. So instead of that, we can use the compressive sensing techniques in order to sense whether the spectrum is efficient to transmit the signal or not, because here the less amount of information will be present, and using that less amount of information, you can use very well efficient cognitive radio in 5G networks. And also wireless sensor networks. So in the wireless sensor networks, basically what is the main criteria of the wireless sensor network is like it will collect the data using wireless nodes basically. So what will happen to this wireless network sensors, if at all, if you want to collect all the data, all the information from each and every place, so it will drain out its power, its battery, and lot of hardware issues comes into picture. So in order to mitigate all that one, if we work on the compressive sensing domain, what will happen is like you don't require to collect all the information. With the very limited amount of information, you can have the complete data using this compressive sensing techniques. So with that one, what will happen is like overall hardware complexity will come down, and power, it will become more power efficient. That's where we can use this application of this compressive sensing. Another one of the major thing in the 5G communications is the multimedia coding and communications. So if you see in the mobile communication, what we do regularly is the voice communication and the video communications. So if we apply the compressive sensing techniques over there, we can have the very high resolution of data with very less amount of bandwidth using this compressive sensing techniques. So as we go on, we will deep dive into this multimedia coding and communications, how we can have the efficient application of the compressive sensing techniques to that multimedia coding and communications. So now if we see that application of the compressive sensing in multimedia for the 5G networks is like, one is video and image processing, video coding. So video and image processing is nothing but we are processing the video signal or image on the image to remove some kind of a noisy characteristics which are present in that one, or some missing pixel informations, so that you will have the better quality. So if we adopt this compressive sensing techniques, where the information will be not available, because once you take the picture, once you send it to the receiver, at the receiver end, you will not have the original encoded content. You will be only having the some content which may not be suitable to remove the noise or denoise it. So if we adopt this compressive sensing technique on that signal, what will happen is like whatever missing data present in that one, you can retrieve it. That is one of the major application in the video and image processing. Another one is the video coding. So video coding is nothing but like we are compressing the video signal in some form where it occupies very less amount of space. In turn, it will take very less amount of bandwidth in order to transmit through the channel. So if we apply the compressive sensing technique in the video coding standard, what will happen is like you can make use of the same bandwidth to incorporate more number of users into the same bandwidth. That's what the video coding will offer here. Another one is the speech and audio processing. Speech and audio processing is nothing but an example I could say here is speech synthesis. For example, many people might have seen the Alexa devices. So whenever we utter a keyword called Alexa, what exactly it will do is it will understand what we are speaking, what the person is speaking. That is nothing but speech synthesis. It synthesizes first and then it will understand what the person is speaking. So if we apply there, because it cannot model all the keywords, it cannot model all the features of the speaker, it is not possible. That is not a realistic scenario. So the compressive sensing technique, if we use in the speech and audio processing for the speech speaker communications or speech recognitions, what exactly will happen is like with the very limited amount of data, you can reconstruct the signal. As such, like video coding, even we will have the audio and speech coding. So whenever we talk on the phone, our samples will not be exactly transmitted to the receiver. So here the coding will happen, because the bandwidth is even though bandwidth they are offering very huge, because of amount of increase in the users in the 5G, what will happen is like it will become very cumbersome, because we are along with the along with the bandwidth improvements in the 5G, it is also offering the very high amount of users. In order to incorporate all those people, all the users into the 5G network, so we should have the proper audio and speech coding techniques there. So going on, we will see that how compressive sensing techniques can be applied in these domains. So now if you take the compressive sensing in audio and speech processing, as I mentioned that speech and audio processing is nothing but like processing the speech signal, and then we are deriving some information out of that one. So some of the main things in our networking or communication related stuff is noise suppression and echo cancellation. So whenever we transmit a signal, so everyone will be very happy to see that it should have the very less amount of noise, and there should not be no echo kind of thing when the person is speaking on the speakerphone. So how the compressive sensing technique can be used over there? So if you want to model a noise, or if you want to denoise a noise which is present in the contaminated speech signal, you should have the characteristics of the noise. So in order to model complete noise characteristics, it is very tough. It is not possible realistically. So using the compressive sensing techniques, where when you have the very sparse information, you can reconstruct the signal. That is what the major feature which is given by the compressive sensing technique. So if we apply this compressive sensing technique in the noise suppression, you can model the noise signal in a better way, and you can remove the noise present in that speech signal. The same way with the echo cancellation. So echo can come in many kind of a channels around. It's like the place where we are sitting, and it matters a lot actually. So how can we remove this echo from that speech signal what we are talking on the speakerphone? So there also you cannot completely model the echo characteristics of the room or echo characteristics of your environment. So using the compressive sensing technique, where it's when the signal is sparse in the sense like when you have the very limited amount of information, then we can apply this technique in the echo cancellation in order to remove that echo in that one. And as I mentioned, the interactive communications, like interactive communication is nothing but speech recognition and speaker recognition. Here, like speech recognition means it does not matter who is speaking, but it matters that what kind of a word is uttered. Alexa, play this song. That's what a kind of a speech recognition. It does not matter that who is speaking to that one. So that requires a modeling of the speech content, how you are synthesizing. So if you want to collect the complete information of the speech, what you want to synthesize over there, it's a kind of a realistically it is not possible. It is very tough to manage that one. If you want to realize that one and realistically without using this compressive sensing techniques and all that one, what will happen is your hardware complexity will grow like anything. It's like it is not a realistic one, because you cannot carry the battery through you wherever you go. So it is very tough. So if we use the compressive sensing techniques for that speech synthesis, where the amount of information present in the speech synthesis is very less, this compressive sensing technique will enable to synthesize the signal very efficiently. Another one is the speaker recognition. The speaker recognition is nothing but it has to identify the who is speaking that one. That is what speaker recognition. Basically, in the speaker recognition, it has to model the speech as well as the speaker. So speaker modeling, it is also it is very tough. In my view, there is no very efficient technique till today in the market, even though this has started some 40 years, 30 years back. Till now, the research work is going here, but we don't have the efficient speaker recognition techniques. So if we adapt the compressive sensing technique to this speaker recognition and speech recognition, we will have the very efficient interactive communications with the machines. Another one more thing where we can apply this compressive sensing in the speech and audio processing is like binaural audio speech processing. So basically, like if you see the regular music or a regular kind of a voice communication, you might be having a mono channel or a stereo channel maximum so far. So if at all, if you want to have the more spatial audio effects, like where exactly the person is speaking, whether he's speaking behind or front, or if there are any blockages, you will have the exact replica of that one using this binaural audio processing. So it requires a lot of amount of modeling information. So if we apply this compressive sensing technique over there, you will get that missing information and you can reconstruct the signal efficiently in order to represent the signal in the spatial domain, so that you will have the more intuitive effect. So these are the some of the things what we think in audio and speech processing. Now, when it comes to the in audio and speech coding, so far whatever we were talking is on the only the processing side. But when it has to be transmitted through the channel, the signal has to be coded, encoded. So one among that means like the basic thing is the speech and audio coding in our voice communications. What exactly is the speech coding? So basically, like when we talk, the samples, if you take the typical scenario, what we do is when the mic captures the speech signal, it samples at the Nyquist rate, whatever it is offering, whether it is a narrow band or wide band. If you take the 4G communications, now it is offering the wide band communications. So it will be sampling at 16 kilohertz, and the bandwidth of the signal considered there is 7 kilohertz. So if you want to transmit as it is, what will happen? For example, I am sampling at 16 kilohertz, and each sample is represented by the 16. So 16,000 into 16 bits for one user, that per 1 second, that amount of data has to be transmitted over the channel. And imagine how many people will be there, how many users will be there. If you try to do that way, what exactly will happen is like congestion will happen, and you will not have the efficient communication. Most of the time, people will be like hearing the user is busy or channel is busy kind of thing. So if you want to have the efficient communications, what one has to do is the speech coding has to be incorporated. So if you take the voice communications, it has incorporated the speech coding techniques in that one. So for the 5G networks, what exactly the codec used here is the EVS codec, enhanced voice service codec, basically enhanced voice service. So if you see the previous codecs, previous networking standards, where we will be using the adaptive multi-rate AMR speech codecs like that. So with the 5G, this EVS codec will be used in this one. So one of the feature for the EVS codec is that it is a very full band signal. Full band in the sense like it is a bandwidth is considered here is the 20 kilohertz. So narrow band means 3.4 kilohertz is the bandwidth, and for wide band 7 kilohertz is the bandwidth, and for the super wide band what we call it is a 14 kilohertz, and for the full band it is 20 kilohertz. So when we see the sampling rates for the same thing, for the full band, when the bandwidth is 20 kilohertz, it is sampled at 48 kilohertz. This is what the full band signal means. So this EVS codec, it supports that one. So the coding technology or coding methodology in the speech codec is basically on this ACLP and MDCT. ACLP, when we expand it, it is called algebraic code excited linear predictive coder, and MDCT is the modulated discrete cosine transform. So basically, like what exactly this ACLP and MDCT will do is it will transform the speech signal, which is in the time domain, into a very less number of samples or very less amount of information in the transformed domain. And this the transformed domain content is transferred to the receiver. And the receiver, using those parameters, whatever has been generated in the encoder, will be synthesized and reconstructed. That is what the ACLP and MDCT. So the another one of the feature of the speech codec is the error concealment. Imagine that one of the speech frame has been lost in the channel for some reasons. So how the speech signal has to be reconstructed. So always this speech coding is a based on the history. It's like what the previous frame. Based on the previous frame, the current frame is reconstructed. Imagine that previous frame has gone. So how we have to reconstruct it? That is what the error concealment technique, which is nothing but a packet loss we call. So this offers very high efficient error concealment techniques. So this EVS codec, even though it incorporates ACALP and MDCT, we can apply this compressive sensing technique in the EVS codec to make it much more efficient. As I mentioned, that full band codec, full band, it means that 48 kilohertz sampling rate, which is not required for the speech signal, because speech signal most of the time it will be like wideband. Beyond wideband will be very tough to hear the content which is present in that one. But when we incorporate the sampling at 48 kilohertz, it makes no sense for the speech signal. But system tells that we have to use that sampling rate. So at the time, what we have to do? So we have to incorporate this compressive sensing system over there in a way that we can optimally utilize that bandwidth, and we can incorporate more users into the same bandwidth with less amount of information. So we will see that how we will be applying this compressive sensing technique in this EVS codec. So I'll be explaining in detail about that. And this is about the speech codec. So when it comes to the audio coding, usually like what we do, the coding methodology is the MDCT over there, modulated discrete cosine transform. In the speech codec using the ACALP, what exactly we will be doing is we will be modeling the speech source. Speech source is nothing but our mouth here. So how do we parameterize? Means like how do we extract the parameters? Using these parameters, you can reconstruct the speech signal. That is what speech synthesis, which is present in the speech coding technique. But when it comes to the audio, if you want to parameterize that audio signal, so the basic difference between audio and speech signal is the bandwidth. When you take the audio signal, music also comes into picture here. So for the music signal, it will have the huge amount of frequency components in that one. If you want to model or if you want to parameterize those music signal, it is realistically it is not possible. So what we will do is we will do some other technique called MDCT. So the time domain signal, it is converted into the TCT domain, and then in the TCT domain, what exactly will happen is energy compaction. Means like the same number of samples whatever present in the time domain need not to have the same amount of signals in the DCT domain. Means like you will have the very less number of coefficients. Using those coefficients, you can reconstruct the audio data. That is what the theory behind the MDCT. So if we efficiently utilize this CS techniques, compressive sensing techniques in both the speech coding and audio coding, you will have the better voice communication or better music communications in the 5G networks. We will see how we will be using these techniques, and how we will be using the CS technique for the typical or without the CS, how we are going to modify this one. Now, if you see that typically this is what will happen in the wireless communication. So in the transmitter, a person will speak the speech, and he will utter something, and let us, for time being, you don't think that there is a compressive sensing module is there here. So just the signal, it is passed through this kind of codecs, voice codec or speech codec or audio codec here. And then once you compress the data using the speech codec, that is transmitted via wireless system, and it is transmitted through the channel could be wire or wireless, whatever it may be. And then in the 5G means like, let us consider the wireless system as our channel. And then once the receiver receives, what exactly it will do is basically it will reconstruct the signal using the sent parameters or sent encoded parameters, and then original signal is retrieved here. So in between, if we introduce the compressive sensing module, what exactly will happen here? So further you can reduce to a huge amount, and whatever you are thinking that it is not possible using the regular communication, that can be possible using the compressive sensing module. Because compressive sensing module, one of the basic feature is signal should be sparse. Means like even if it is having the very less amount of data, less amount of information, still you can reconstruct the signal at the receiver side. So you can send the huge amount of what you say effects or huge amount of methodologies, whatever the user wants to transmit to the receiver. So if we incorporate this compressive sensing in this wireless communication, you will have the better transmitting criteria. Now, if you see how this speech codec will be there in typical speech codec, this is without any compressive sensing. So if we add the compressive sensing module, we'll see how it will look like and what it is going to offer. Now, if you see the typical block diagram of any speech codec, it will have the basically input signal. The input signal is characterized, or it extracts the parameters from that speech signal. So if you take any speech signal, what are the main important characteristics will be? It will have the one envelope, one kind of a envelope. It means how the signal looks like in the time domain. That is what the envelope, what we say. And then the resonance present in that speech signal, that is called pitch. So pitch is unique to the persons, and then the pitch is nothing but a resonating factor in that speech signal. So if you know the envelope information and if you know the pitch information in the speech signal, you can reconstruct the signal at the decoder or at the receiver side. So that is the basic funda or simple technology behind any speech codec. Now, if you take any human person, so the air comes from the lungs and it passes through our throat and it comes out of the mouth. So this is the basic thing what will happen, how the speech signal is generated from the human being. So in this one, what we are trying to do is we are trying to model the vocal tract, means how the signal is generated, articulated here and got out of the mouth. This is what will happen in the speech codec. And if you model that one, modeling means what? We are extracting the parameters in order to represent that one in our softwares. So if we try to get the parameters, what exactly will happen? Synthesis is a matter of reconstruction using those parameters. So now let us see how this parameter extraction is happening and what parameters it is generating. And if we incorporate the compressive sensing system here, how it is going to reduce the complexity. That's what we will see now. Now, here the input signal is nothing but your air which is coming from the lungs. When it passes through your vocal tract, it is a kind of a pre-processing, and then you will get a kind of an envelope to that one. And also it will add pitch information. So that is what will come out of that one. So now if you want to model that signal, first let us see how we are extracting these parameters. So this input signal, it is pre-processed in the sense here we will be using second order IR filter, which is nothing but a band pass filter. We will be limiting depending on our criteria. For example, if it is a narrow band, we'll make sure that bandwidth will not go beyond 3.4 kilohertz. If it is a wide band signal, we'll make sure that pre-processing filter, it will have the 7 kilohertz bandwidth. If it is a super wide band, 14 kilohertz. If it is a wide band, it is a 20 kilohertz. So that you can tune it actually. So usually for the speech communications for the wide band, up to wide band, we'll be using second order IIR filter. So once you get those coefficients, using the MATLAB, you can generate those coefficients. If once you give this, what exactly you want to derive it, if this is what my low pass filter or band pass filter. So if at all, if I want to have these characteristics, this is what is my band pass domain and this is what the gain I require. If you give to that MATLAB has inbuilt filter generating functions where it will generate the coefficients and it will give it to us. So that is what, using those coefficients, you can do the pre-processing here, which is nothing but band pass filtering here. So once you get that band pass filter, means your system is ready to analyze now. So here the thing is basically the speech, it is not a continuous in the sense, what I mean to say here is it is not in terms of domain what I'm talking. So you will not expect that what a person is speaking later point of time. So even it is very tough to take the complete speech information and model it. That is not realistic. So while talking itself, it has to compress and it has to model it and it has to send it to the receiver. That has to happen. So in order to happen that one, your input signal is analyzed in a frame by frame basis. That is called the frame size, what we call. Usually in the AMR speech codecs, what we consider as the 10 millisecond, 16 milliseconds, 10 milliseconds, like that we will consider. So here we consider as a 16 millisecond buffer size. So it depends, it varies depending on the codec what you are incorporating. So once the frame size is fixed here, once it passes through the pre-processing, so you have the content now, which is a band pass filter, and you will be extracting the parameters using these modules. So as I mentioned, the speech signal will have the envelope and pitch information. Envelope is parameterized, or in order to generate that envelope information, LP analysis, linear prediction analysis, what we call. Linear prediction, it is a kind of a normal FIR filter, a 10th order filter we use in AMR speech codecs like narrowband. If you take the wideband codec, you'll be using 16th order FIR filter. So using those FIR filter, you can generate or you can construct the speech signal. Speech signal in the sense like only envelope information. So once you get that envelope information, so whatever signal you got it from here, okay, once you subtract only that envelope information, what will happen? It will have only the pitch information, because you are generating the envelope here and you are subtracting the original signal from here. If you see here, this is the path of the original signal and this is the synthesis one. So once you subtract it, you will have only the envelope information in that one. Sorry, pitch information. Because this LP analysis, what it will do is it will generate the envelope information. So now if you try to estimate the pitch, then if you subtract that one with the signal, then envelope is subtracted and the pitch information is also subtracted. What it is left out? It is left out with nothing, basically, if you understand. Otherwise, like basically in the real-time scenario, that is not correct, because you will not have the precise hardware or precise thing to estimate the things. So still there will be some residual part will be there. So that residual part will also be taken care while coding. So now once you are able to, let us consider that you are able to represent your envelope efficiently, means like you have the coefficients here now. So those coefficients are nothing but your LP coefficient, linear predictive coefficients. They are the parameters which are used to synthesize your envelope of the signal. And once you get the pitch information, so this is what the pitch analysis it will do. Basically, like once you get the perceptual weighting, means is nothing but you will get it from the LPC filter, and then you will apply that kind of a gain over here. And then the pitch analysis, what it will do is, as I mentioned, LP analysis for the envelope and the pitch analysis for the pitch information. So once you get the pitch information, you will use the adaptive. There are two code books here, fixed code book and adaptive code book. So adaptive code book is basically has a certain amount of information which keeps adapted over a period of time. So this pitch information, once you get this data, it will update in the adaptive code book. So that adaptive code book, whatever is generating here, it will transmit it. It will create a index of that one. Means it is basically a kind of a pointer to that address book. Okay, this is the pointer which you need to take, and that pointer will be transmitted to the receiver. At the receiver side, what it will do, it will just refer to that index, and it will get that whatever is present in that index, that is the pitch information present at the receiver side. So as I mentioned that once you cancel this envelope information and pitch information, you are left out with some kind of a noisy signal. So that noisy signal will be coded using the fixed code book. So now if you see here, this 10 coefficients and the pitch information is nothing but the adaptive code book, and the residual information is nothing but the fixed code book, and some gains which are related to that one. So how much gain it has to be there. So those gains you will estimate it. And for each thing, here 10 coefficients, one pitch information, there is nothing but your one index, one fixed book index, and one these two gain values. You will be, these are the parameters which are present in the speech codec, and you will be transmitting this to the decoder side. So before sending, what we will do is we will quantize it. We will quantize and we will share it with the receiver side. In the receiver side, exactly what will happen is it will not have these things. Pre-processing LP analysis will not be there. It will have only the synthesis filter, adaptive code book, and fixed code book, and gains. That's it. You don't require all this one. These things are only required for the encoding purpose. For the decoder side, just if you give the parameters to this one, for example, once you estimate the pitch information from the encoder, and if you transmit that index to the decoder side, it will just check that address pointer and it will get that value. That's it. And for the same thing for the fixed code book. So using this synthesis filter is nothing but inverse filter of the LP filter. So whatever filter coefficients you are having here, if you do the IR filter, here it is an FIR filter, it is becomes a IR filter over here. So that's it. If you have these things, you can reconstruct the signal. So this is the basic block diagram of the any speech coding technique. Any speech coding technique, if you take AMR, NB, AMR, wideband, EVS codec, whatever you codec you take for the speech related stuff, this is the major block diagram. Now, if you see how, if we apply the compressive sensing technique here, what will happen is like we will have the complexity will be reduced here, and also you'll have the amount of information, whatever is represented, it will become very less here. We will see that how we are going to incorporate that compressive sensing technique in the speech coder or speech codec, whatever we have discussed so far, and how it is going to reduce, we will see it. Now, if you see here, here we have added the CS enabled. So here, first of all, what first step in the compressive sensing technique is, first of all, we have to transform the signal which is sparse. The domain should be, in the domain, signal should be sparse. That is what this block is about. This is the input speech where you are transforming that speech signal into the domain where the signal content is very less. So similar kind of a analysis will be here. LPC, formant synthesis filter is nothing but pitch filter. So the same kind of a techniques will be there. But here, if you see here, you are operating on the complete samples. Here, what we are doing, we are operating with the less number of samples. So overall, what will happen? Your transmitted content will be very low. Means like the size will be very less. Even for example, in the input signal, if we assume that some of the speech content is missed, because of the sparseness in the signal, you will be in a position to retrieve it. That is the major feature of the compressive sensing technique. So once you transmit those parameters to the receiver the same way, like LPC codebook index is nothing but your fixed codebook index, and then those indices, based on that one, you will be generating the parameters. Once again, you have to do the reconstruction. Here, you have done the compressive sensing technique to the input signal. The same thing, in order to reconstruct that one, you have to follow all this one, like generation of that sparse signal domain coefficients. This is nothing but sparse, what you say, generation of the sparse matrix, we say. It's in the form of the matrix. Basically, like if you want to realize in the softwares, we will be operating using the matrices. So once you generate the sparse matrix here, what exactly will happen is like you will be doing a reverse engineering what you are doing in the input compressive sensing domain. So then once you do the recovery, you will get the original signal here. So here what exactly has been done is like we have added this compressive sensing domain module, and overall the transmitting values will come down. Means like the parameters will come down and it will be more efficient. But there is a one drawback here is like we are adding one extra compressive sensing module here at the decoder side. Also we are adding some modules in order to reconstruct that one. But because of the growth of the VLSI technology, we are having the very efficient hardwares in order to incorporate these compressive sensing modules in the speech communications. So this way, compressive sensing can be used in our speech communications in such a way that it will become more efficient. Now, if you take, this is so far whatever we have discussed is on the speech codec side. Now, let us see a small thing on the audio codec also, so that our discussion will be holistic. Because as I mentioned that speech can be parameterized. If you see here, speech can be parameterized. You are parameterizing, means like you are designing your throat, or you are creating a throat the way like how it is coming. This is what we are doing. But here, when it comes to the audio, you cannot do that one, because you have the lot of frequency components in the audio content, because it will have the music and all that one. So music will have a lot of, for example, if you have many instruments and all that one, what exactly will happen is like it will give the more amount of frequency components, a different frequency. So those kind of frequency, if you want to reconstruct or if you want to synthesize, that ekal coder or whatever the speech codec is not capable of doing that one. Instead, what we do is we will try to transmit the same samples to the decoder. But as I mentioned previously, like if you take the sampling rate as 48,000 samples, and each sample is represented by 16 bits. So for one channel, 48,000 into 16, that much amount of data you have to send it per second. That is what I'm talking about for one channel. Let us take two channels. What exactly will happen? It will be doubled. So it will not be efficient to transmit like that. So here, what exactly the audio coding will be done is like there will be a kind of an analysis filter bank. That is what we say as MDCT. If you see here, it is basically like all audio coders will be like based on the MDCT. MDCT is nothing but modulated discrete cosine transform. It is a cosine transform, DCT. So basically this analysis filter bank is nothing but your DCT. That is what we call as a modulated discrete cosine transform. So this will transform your analog data, your time domain data into coefficients of the DCTs. So, but if you are going to transmit as it is to the decoder, what will happen is like it will be more amount of data will be present. For example, there are two sounds. I'm giving an example here. Like take at the same time, I'm talking and background there is very huge noise is coming. What exactly will happen that if the noise level is more than my amplitude level, that noise level masks my speech data. So overall, when you transmit to the decoder, what will happen? You will be receiving only the noisy content. Is there any way that why speech has to be transmitted to the receiver? I don't think it is required, because anyway, the receiver is not able to hear that one. So what is the point of encoding that speech content or whatever the content which is masked by the other signal content? It is not required to transmit. So this perceptual model, what it exactly designs is that which signal component can be considered, which signal component can be ignored. So the redundancies can be removed using this perceptual model. So once you have the DCT coefficients output here, and once the modeling is done, means like which sample as irrelevant. For example, when I am quantizing, you will be having some kind of a background noise. So if your noise is lesser than that quantization noise, what will happen is like you don't hear that noise at all, because your quantization effects comes into picture over there. So what will happen is like it is not required to consider that sample itself. You can just ignore it, so that overall space will be come down. So using this analysis filter bank and perceptual model, and then once you get the output of this one, this is a kind of an iterative process. So you have to see that whether my output is correct or not. This is at the encoder side. Once you have these coefficients which have the removed redundancies based on this perceptual model, it is called also psychoacoustic model, what we say in our terminologies. So basically, like how your brain is perceiving those signals, that is what is been designed using this perceptual model. So using that one, we will remove the redundancies. Once you have the proper coefficients, what it will be done is like we will be quantizing and we will be sending it to the receiver. So this is what the bitstream encoding, basically like bitstream encoding is nothing but the Hoffman encoding, what it is called as a lossless we call here. So using the Hoffman encoding, still we can further reduce it and we will transmit it through the channel. And from the decoder, same thing, it's a reverse process from here. It's a bitstream decoding. It means Hoffman decoding is done here, and then inverse quantization. There won't be any perceptual model in the decoder side, because you have sent after analyzing to the decoder. So the decoder, with those coefficients, it will just reconstruct the signal and it will give the output. So now where we can apply our compressive sensing technique here. Now, if you want to model this perceptual model, it is not that much simple. It is a very complicated process. So if you have the very less amount of data, if the signal is sparse here, before giving it to here, if the signal is made very sparse, what will happen is like your perceptual model will become more robust, and the amount of quantity present here, it will become less. In the overall bandwidth will come down. That's where one of the what we can see is that usage of the compressive sensing technique in the audio signal communications. So far we have seen that how the speech communication and audio communication will be very well utilized using the compressive sensing techniques. Now, if you see the how this speech codecs means like in which standard what is used, we will get a kind of a better understanding of the codecs what we are using. If you take the GSM, like in we were using the enhanced full rate codec, which works on the narrow band. So the maximum bit rate what it was happening was 12.2. But if you want to send the samples as it is, what will happen? 16,000 into 16, that is per second. It will be much higher than this one. It's like almost 10 times or 15 times lesser than what exactly it has to transmit. Even the quality of the signal may not be as exactly, but perceptually you will not be able to figure it out what is the difference that will be there in this one. So when it came to the 2.5G or 2G, 3G communications, we have been using the adaptive multi-rate narrowband speech codec as well as the wideband codec. Wideband codec is basically what I meant was like basically when your bandwidth is to 7 kilohertz, it is called wideband codec. That is what is being used in the VoLTE communications. Whatever we are seeing in the 4G, the VoLTE, that is using the wideband or high definition voice, what we call. So in 3G, we were using AMR NB and AMR WB. And even to some extent, we are also using the extended versions of the adaptive multi-rate codecs in 4G communications. When it comes to the 5G, we are using the EVS codec, which is nothing but enhanced voice services. But the technology behind this one is the same. Same in the sense they will be adapting to the same kind of a this block diagram. But what exactly happened over the period of time is like there are enhancements happened here. There are extra features has been introduced in order to make it more perceptually quality the signal. That's what has all happened within, but the basic block diagram will be remains same. There won't be any change in that one. Here, if you see here, the data rates has come down or whatever it may be. If you see here, so the data, how come these data rates are coming down? Because there are some enhancements happened in that basic block diagram. That's what has happened. So if you see, this is what the speech codecs evolution over a period of time from starting to till now. So if we use the compressive sensing techniques, you can use anywhere. It is not only meant for the 5G. You can also use for the 4G. You can also use for 3G. Wherever you are interested, we can use it. But we also need to see that whether the system allows or not. If the system is not capable of allowing that one, then it will become a tough there. So why we are thinking that compressive sensing technique will help in the 5G is because it's a newer technology where you can incorporate the new technologies along with this one. So what will happen is like incorporating of the compressive sensing techniques in the 5G will become more easier, and also because of the improved hardwares, you can easily realize the compressive sensing techniques in the 5G networks. So far what we have discussed is on the compressive sensing technique, what exactly it is, the technology behind, and what we will be doing, and what are the applications, all that we have seen. But if you want to realize all those things, you should have a proper processor or a proper hardware, how we can realize that one, because 5G it is offering many features. I say like it's like by seeing itself you will see that it is very tough to realize all those things in the realistic, but there will be a kind of a architecture has to be developed, or a specialized hardware to be developed in order to realize all those features. So let us see the concept of this architecture, hardware architectures, how we can realize whatever we have spoken so far. So the main features of the digital signal processors for the 5G or even 4G also, they will be using the same thing, but there are many enhancements has happened in the 5G architectures. So basically like the ALU has become much more complex. Because of the many mathematical operations comes into picture, the LU becomes very complex. It is not that much simple. You have to, previously we used to talk in megahertz and all that one. Now we have to talk about tera, means like previously like MOPS we used to call million operations per second. Now it has to offer tera operations per second, because if you want to realize all the features whatever we are trying to see in the 5G, it requires very huge amount of calculations or huge amount of mathematical operations. So for that one it requires complex ALU, for example. And for the speech communications or speech synthesis, basically what I mean to say, speech synthesis usually it incorporates neural networks model, that is what we call as a machine learning engines. So a specialized machine learning engine has to be added to the 5G processors, otherwise we cannot realize all those things. And also there should be a lot of parallelism should be enabled in the 5G processors, and also it should be very low latency. Means like, what do you mean by the low latency? Here is like low latency is nothing but your output should be in a realistic time. It cannot, for example, if I ask something now, it cannot give after a something like 5 minutes or 10 minutes kind of thing. If I ask something, it has to give immediately. That is what low latency means. Like the output should be in the realistic format. And one more feature of the 5G or any processor for that matter, it should be very low power. It cannot drain your battery just like anything because I'm offering all these features. It should not be like that. It should not compromise on the power as well. So it also should be having the very low power. And also in order to realize this low latency part, you should have the very fast memories. You cannot have the very slow memories here. So these are all the main features what one can consider for the signal processors and for the 5G. And also it should be scalable, of course. You have to run any algorithm on that one, or you can enhance just like that without modifying the processor. That's what is one of the major feature of the DSP processors, which are meant for the 5G. So when you incorporate these things, the processor will become so powerful. So let us see some kind of how the exactly this digital hardware will be present, and then how these processors has been enabled with the new architectures, how they are going to be realized. We'll see a kind of a basic things here, and then if you see here, this is a basic block diagram of the any wireless mobile architecture. Here if you see, a speaker will be there for the phone, and then mic will be there. So the data, this is basically speech and audio data which is given to the codec. A codec is nothing but coder and decoder. What exactly it will do is like the way like what we have discussed previously, like it will generate the parameters, that it will do the MDCT and everything, that will be taken care by this codec. And then camera data. This is a kind of a, what you say, visual data. So all this one will be a kind of a input to your mobile system. It's a kind of a CPU, what I say. It will have the two processors. One is the application processor, another one is the DSP processor, what we call is a baseband processor also. So application processor is like very powerful engine. But it is not power efficient. So whenever you want to watch any movies, or whenever you want to watch any videos, whenever you want to hear very high resolution audio content, then the application processor comes into picture. Otherwise, it will be in a sleeping mode. All the time it will be sleeping. But there will be one processor which will be always in a wake condition, because whenever a call comes, your mobile has to answer that one. So that is done by your DSP processor. Means like all your speech algorithms or speech codecs will be running on the DSP. So if you want to have the better speech processing or speech coding techniques, your DSP should be very efficient. So usually like application processors mainly comes from the ARM, and the DSP is from the their own proprietary. Like for example, if you take Qualcomm, they have their own DSP chipsets. Like Snapdragon is a platform where it will have the application processor, where it will have also have their own DSP, and also it will have the analog to digital, digital to analog conversion modules here. And then the same thing here, it will once you get the data, it will be like it will be done transmission, and the receiver part it will be receiving, and then once again the reverse processing will happen. So this is the generic wireless mobile architecture. Here we will discuss majorly on the DSP side. We will don't go the beyond that one, because it will take its own time, and it is beyond the subject of discussion. Now, if you take, this is one of the chipset which is released for the 5G from the Qualcomm. So, as I mentioned, that it should equip with the very low power. It should offer AI accelerators. This is nothing but ML function accelerators will be present as part of this Qualcomm chipset, which is 865 model, which is specifically meant for the 5G communications. So these will be, they have their own accelerators, in the sense like those AL modules are created out of the hardware. There is no software running for that one. So you can directly use, hardware will be much faster compared to the software. So if you use those accelerators, you no need to worry on the software part. Means like even though when you are realizing or when you are doing prototypes, you will be doing in the software side. But when it goes to the hardware, you don't require to use all those modules. You can just simply call the AI accelerators. So it is, compared to the previous processors, it is very much efficient by 25% like that. And also it offers very high download speeds like 7.5 Gbps kind of thing. And also it will have the cognitive radio thing, like that's what's dynamic spectrum sharing or sensing. And then it also offers very high video related processing capabilities. It also offers very gaming. It's more for the gaming as well, because the gaming requires very high resolution of data and high bandwidth. So this is the processor which has been introduced by the Qualcomm in order to it can be used for the 5G related communications. So when it comes to the application processor, or even not only the Qualcomm, even the many other DSP vendors like NXP Semiconductors and Huawei, and many players are there in the market. One among that one is also the ARM processor. Like ARM processor, they will do the application processors as well as the DSPs. So if you see the architecture, internal architecture of this ARM processor, what exactly it will have is like, basically, if you see the latest ARM processors, it works with the 32-bit as well as with the 64-bit. So basically, like, it will have some security features. Like, this is what a trust zone, what we call trust zone, is basically which enables the security features. For example, when you transmit the signal, or when we want to work with the in the secure environment, for example IoT, when it comes into picture, what exactly will happen is the security comes into picture. So this trust zone is a dedicated hardware accelerator which is present in the ARM, which will enable for that security features. And also there is something called Neon Engine, which is nothing but your powerful vector processing unit. So using this Neon Engine, you can process your data seamlessly with high resolutions. If you see here, this is what nothing but this trust zone and crypto. These are they are closely related basically. So crypto is nothing but for your secure communications. So when it comes to the older architecture, it only supports 32-bit architecture. But when it comes for the latest processors, like whatever they have been, as I mentioned that in the Snapdragon, basically this is the DSP from the Qualcomm. But when it comes as a platform, it will come with the application core as well as the TSP. So for the application cores, you should have these kind of features. Like it should support very high processing, vector processing related stuff, and your algorithms may be like more of a floating point. Like most of the time, in order to realize our algorithms, we will be writing the floating point code only, because in order to convert into fixed point code, it will take good amount of time. So since the VLSI technology has evolved, so we can use the floating point units at the low powers. So this is the basic architecture for the ARM. So, but when you see about the processor which is being released for the 5G from the ARM is Cortex R8. This is the first processor from the ARM processor where they have released specifically for the 5G. So one of the important feature in the 5G is that low latency communications, right? So for the low latency communication means like your output should be in a very low latency, means like it should come just like in a, what you say, in a specified timing it has to provide the output. So basically like Cortex R series processor is nothing but real-time processors, what they are calling. So this can be used for the low latency communications. If you see here the basic thing, like this is a main CPU, and then this is a floating point unit. There will be a separate floating point unit will be there where you can do the floating point operations, and then there will be a separate memory unit which will manages the input output memories, caches, etc. So it also equips with the cache memories here, which are very fast memories which are present in the ARM processor. And also it comes with the Snoop control unit. Snoop control unit is basically like it manages the your cache mechanism, how the memories will be read, write, everything will happen through this Snoop control unit. Because if the Snoop control unit is not efficient, your cache misses will be more. So when the cache misses are more, you will see the more amount of cycles. Means like it is not so realistic. So all this hardware, which is a part of the Cortex R8, it enables the 5G communications. This can be used as a DSP as well as the application core as well. So far, whatever we have discussed is like I have introduced the concepts of CS, compressive sensing, and where all we apply that one, and what are the principles behind that one, and what is the role of compressive sensing in 5G. We have discussed that one, and also we have also discussed the specific topic of application of compressive sensing for the multimedia signal processing and coding in 5G, and the specific processors which are related to the 5G. We have discussed all those things. So yeah, that's all from my side. And if there are any questions, we can take those questions. So I'm open to the questions. Attendees can pose the questions if they have any on the topic.
Thank you, sir. Thank you for giving the valuable insight on compressive sensing and multimedia signal processing for 5G. Now I'll check with the any queries are there with respect to the participants are there. If any queries are there, you can answer. Right.
Please. Yeah. Thank you.
I'll verify with that. Participants, if you have any queries, you can ask through chat box. And also fill the feedback form for this session. Link is also provided in chat box only. Any queries? No, sir, they didn't ask any of the queries related to this session. And they gave
Sure.
compliments
Yeah.
like a very nice informative session and informative and interesting session and all.
Thank you.
Yes.
So if there are any questions later point of time, you can also reach out to me via my email. Maybe you can also share my email ID.
Yes, sir.
Yeah, and I thank you to the SVC, the Department of EC for taking these efforts and providing me the opportunity to provide the small insights into this domain.
Yes, sir. Thank you, sir. And
Thank you.
yeah, sir, I am sure that your address will help a lot in understanding related to compressive sensing and multimedia signal processing for 5G. And on behalf of Department of E&CE, I take this opportunity to thank our management, AICT, authorities, principal, head of the department, staff members and participants for smooth conduction of this event. Thank you all once again, and we look forward to an extremely productive 1 week feedback. 1 week STTP. Thank you. And ladies and gentlemen, let us break the session and we will rejoin in the afternoon for the day 1 second technical session on compressive sensing techniques for next generation wireless communications by Dr. Jijes, Associate Professor, Department of Electronics and Communication Engineering, SVCE, Bengaluru. I request all the participants to subscribe to our YouTube channel, STTP ECE SVCE, and also click on the bell icon to get notification of next session. Easily you can get into our YouTube channel and also get into our live streaming easily by clicking onto the bell icon. You will get the notifications. Thank you once again, everyone. We'll get back in afternoon session. Thank you, sir.
Thank you very much.